Dear Reginasailing family and friends, let's sharpen our pencil for our second exercise with sun reduction. This is actually the best sharpener that I know of. This is the second exercise because if you should know anything about celestial navigation, doing a sun reduction, sight reduction of the sun is really the most important or crucial part, and the one that you will be using the most, I think, when you are using your sextant. And by this I have my template. The template should be straightforward, and you should be reminded, even if you don't use it for a year, how you go through 1, 2, 3, 4, 5 steps. So let's do a second example. It's close to midsummer, 18th of June, and that's why we are in Sweden. We have left Bornholm and are on our way to Gotland. So by dead reckoning, we have found that our latitude should be somewhere along 55 degrees and 59 minutes north, and our longitude we have estimated to be 17 degrees and some 37 minutes east. Well, that's why I do this second example, because we have easterly longitude, so it's a bit different here. Not more difficult, but a little bit different. And these are very approximate, so we don't need to use these for our chosen latitude and longitude. They will change anyway along the way, because we don't know exactly where we are, and this is the best we can assume, and then we have to pick one which is good enough to find the information in the sight reduction table. And what is the sight reduction table made for? It's made for a full degree of the latitude and a full degree of the local hour angle, which is the angle from the boat to the sun. But this is how far we get right now. So let's say we have been on deck, we've shot the sun in the afternoon, let's say 13 o'clock and 43 minutes and 14 seconds. The log can be something 1, 2, 3, 4. This is only that if you shoot 2 times, one in the morning, one in the afternoon, so you then know how far you have sailed in between the 2 shots. The running fix, the transferred position line, which we will cover in another chapter. And then the course over ground, that is, well, we are on the way to Gotland, so let's say we are about on 60 degrees, and we are not sailing so fast today. We have some 6.0 knots. That is also only to know in which direction we should move the position line. Some might think, why do I write course over ground and speed over ground? Where do we get these from? And I sometimes get the question, do we take these from the GPS? Of course not. We are not using the GPS. That's the whole idea of this beautiful exercise. But I still write course over ground and speed over ground, because it should indicate that we should estimate our movement over ground and our speed over ground as good as it gets. So if there are any currents involved, currents with us or current against us, we add or subtract that in our knots. And if we have any currents from the side or any leeway, we have to estimate as good as it gets to get a course over ground. It's dead reckoning really after all. So the sextant angle we have shot, let's say it was 44 degrees on the sextant and 41 minutes on the drum. So we'll just go through the way now, the simple way we let aside. We assume that my sextant has a index error of 4 degrees off the arc. So if it's off, we have to put it back on. So we add 4 minutes, given here 44 degrees and 45 minutes on the sextant. Next up is the dip. The dip has to do with the height of eye. The height of eye is always the same. If you're sitting on deck, you know your boat. On my boat, it is 2.8 meters above the water level. we can look it up on the yellow pages. So 2.8 means we have to correct by -3 minutes. So we write -3 minutes. This figure and that figure you will most probably know by heart by now, and I can see that I think you have already got the idea of the whole thing. So you deduct these 3 minutes, so we get an apparent altitude of 44 degrees and 42 minutes. This is how far you can do it by heart, so to speak. The sun correction is more difficult to remember because that has to do with the apparent angle. Here it is. So you look it up on the yellow pages. It has to do with the little bit the parallax, but that's not very big by the sun with the sun, but a lot with the semi-diameter and of course the refraction. So we are in April to September, so we stay on this side. We have shot the lower limb of the sun, which I take for granted. So that's why we go for the first bigger figure, disregard from the smaller figures. And then we look at our apparent angle, which was here, 4 degrees 45. So 44 degrees 45, it's quite far down. We are somewhere here, 44 degrees in between those two. So we have to add 15 minutes, okay? So we add 15 minutes. So by doing that, we get a true altitude of 44 degrees 57 minutes. So that's how fast this goes. Let's go to step number 2. Choose a latitude as close as possible as this one. Well, 55 degrees 59 minutes, there's not much to talk about. That is 56 degrees 00 minutes, because that book is only valid for full degrees, so no minutes please. We are on northern latitude. It's red, it jumps down here immediately. Then the declination that we do by eyeball between 13 o'clock and 14 o'clock. It's about 3/4 of an hour into 14 o'clock. So let's look at the eyeball of the declination on this day, 18th of June. So we have to find the 18th of June. 18th of June is here. 18th of June, and it is between 13 o'clock and 14 o'clock. 18th of June, 13 o'clock. There, 13 o'clock. We have a declination of north 23 degrees. Oh, that's a really high declination. Well, it's midsummer after all. That's as far north as it gets, almost 23 degrees and 25 minutes. And at 14 o'clock, it's 23 degrees and 25.1. So it's still on the way up. The declination is still increasing. Well, after all, it's not midsummer as yet. Midsummer is 21st of June. So it's a little bit going up. So never mind those .0, .1. So let's call it 23 degrees and 25 minutes northern declination. So that's 23 degrees and 25 minutes northern declination. With the Greenwich hour angle, that is the longitude of the sun, we can't be that eyeball navigation wise to look between 13 and 14 o'clock, because the sun is rushing around the earth from east to west. So here we have to look at full hour first, 13 o'clock, and then we take the increments for the 43 minutes and the 14 seconds. So let's start looking at the Greenwich hour angle of the 18th of June. Maybe I should make a mark here. 18th of June, full hour, 13 o'clock, 18th. So at 13 o'clock we have a Greenwich hour angle of 14 degrees and 41 minutes. So we have just passed that the Greenwich hour angle has been 0, because we are in the afternoon. So we are just in the afternoon, 14 degrees and 41 minutes. And you can see how fast it moves here. Well, for each hour 15 degrees, doesn't it? 14 degrees and 41 minutes. So I write here 14 degrees and 41 minutes. Now how about the increments? The increments have to do with the 43 minutes and 14 seconds, which we mustn't forget, because it is almost 14 o'clock. So that we do in the very back of the book here. So we look at 43 minutes. This is all valid for 43 minutes. Here are the various seconds. So we have 43 minutes and 14 seconds. 14 seconds. Here, 14 seconds. Ah, somebody's been there before. All right, sun planets, that's where we are. So that's 10 degrees and 48.5. So let's call it 49. 10 degrees and 49 minutes. So this is for the full hour. This is for the 43 minutes and 14 seconds. Another 10 degrees. So we add these two together. So 9 plus 1 is 0. And 4 plus 1 is 5 plus 4 is 9. But for each 60, you get a full degree here. So that means that this is a 3 and a full degree. So 1 degree and 30 minutes is exactly these 9. So we add these together. 4 plus 1 is 5. And that's 25. So the Greenwich hour angle at 13:43:14 is 25 degrees and 30 minutes. Now we want to choose a longitude, so the LHA gets a full number. Now let's do a little drawing here. So the sun has just passed us, 25 degrees, it's just past us. So this is approximately where the sun is. This is the North Pole. That is the meridian. So the sun has passed the meridian. So this angle here is 25:30. And we are at an easterly longitude. So we are actually somewhere here. So I'll draw my boat over there. That's the mast, that's the boat, that's the idea. So the local hour angle is from the boat to the sun. So that's from the boat to the sun. So this is the local hour angle that we have. So you can clearly see, so we have to add the Greenwich hour angle of the sun with our own latitude, which is east. So these two together become the local hour angle. So that means we have to add something here. So what do we add? So this becomes 0, 0. So if we have 30 minutes here and want to get to full degree, we have to add another 30 minutes, because this plus that becomes this. So see here, 0 plus 0 is 0, 3 plus 3 is 60, so that is 0 here, and it becomes the full degree here. Don't forget this full degree when you add. Now, what do we write here? We write a longitude here, which is as close to our approximate longitude of 17 degrees and 37 west. Well, if you are only allowed to write 30 in the back, well, that is very easy to determine that 17 degrees and 30 minutes is very close to 17 degrees and 37 degrees and 37 minutes. So you add these together. So we have 1 here. So we add 5 plus 7 plus 1 is 3, 2, 3, 4 makes 43 degrees. So 43 degrees is our local hour angle. That's good. So that is what we can go into there. Before we do that, we can see that we have had something red here. One more gain. 17 degrees and 30 minutes. That is our chosen longitude. 13 degrees and 30 minutes east. And our latitude is northern, of course. So now we go and find our page in our sight reduction table. We look at the working latitude, which comes from this orange arrow, 56. Well, I have it here. 56, so that makes sense. So we can tick this off. Same or contrary? Well, the sun is on northern declination. We are on northern latitude, so this is the same. So we go for same, tick, same, tick. There we are. Okay, declination range. Well, we have a declination of 23 degrees it's between 15 and 30, 15 and 29 here, tick there, 15 and 29. So that's the correct page. So always check 1, 2, 3 that we are on the right page, because that is also a possible error that you pick the wrong page in the sight reduction table. Now what do we do here now? We look for our declination. The declination, the full declination is 23 degrees. So that is here. So that's the declination of the sun we're looking for. And we look at the column of the local hour angle. So please note that you have local hour angles which are very big numbers here, and local hour angles which are very small numbers there. So these have the same angle. And that is what I tried to say yesterday. It doesn't matter if you are here and the sun is there, or vice versa. So the angles are the same if you take this local hour angle or if you take that local hour angle. So that's why they have compiled this book again to make it as efficient as possible to have the local hour angles on both sides. So when we are looking for the local hour angles of 43 degrees, we have to check on what side can we find it. And in this case, 43 is found over here. 43. So that is the local hour angle. And now we try to find these where these two meet. So that is how I always do it. That's the second lowest row. So I go over here, the second lowest row, and that is this one here. I'll try to show you once again. You go from 23, you go down somewhere where you have a local hour angle of 43. That's the second lowest of this box here. Can you see that? So you go over here, so you mark the second lowest of that box. We have three figures again. That is the figure for HC, D and Z. And HC is 44.27, D is 51, and Z is 116. No, 118 it says, 118. So we copy these three figures. We copy them over here. We have an HC of 44 degrees 27. That's almost the correct angle, the calculated angle that we should measure. Almost, because this angle is only, this altitude is only valid for the full degree of declination, because we have gone a full degree of declination. We haven't been in between here. But the declination have some minutes as well, and these we take care of over here. And D is the weight, how much we should take that into consideration. That is plus 51, that's the weight. 51/60 as you can remember. Plus is, it would have said minus here otherwise, but I can reveal that plus, it's always plus when you have the same here, and minus if you have contrary. Why? Because if the declination is has a bigger figure, has some minutes here, that means that the sun is closer to us, and that means that we should really measure a bigger angle. Whereof if this had been on the southern latitudes, meaning that the sun had a southern declination, then a bigger minute here, some minutes additional to this full degree, means that the sun is even further south. So the minutes that we have to take into consideration means that then the sun is further away. So that means that we should measure a smaller angle. If you didn't quite follow that, never mind. It's very easy to have a plus there to copy from over here. And all I wanted to do is to explain why you would get a bigger angle if you have some minutes to take into consideration of the declination, because the sun is closer to us. And the Z, well, I was talking so much I forgot what the Z was, 118. So what do we want to do first? We can decide either we go to the azimuth or we correct for the angle. Let's correct for the angle. So that is 44 degrees 27. That's what is valid for the full degrees of declination. Then we have to take these 25 minutes into consideration and 51/60 of them. And again, here we have the wonderful table 5. Table 5 is here that you look at the D factor. The D factor is 51. D factor is 51. That's over here. And the minutes in question is 25. We go down there, 25. And where these two meet, it says 21. So this is the weight, and these are the minutes, 25 minutes. And you can see if the weight is 60/60th, you take the full 25 minutes into account, and if it's only 10/60th, well, then you only take this part of the... So the numbers get bigger and bigger, the more weight there is, the more we have to take them into consideration. So 51 as the D factor, 25 minutes means that we have to add a 21 over here. We add it nicely. So we add these together. So that becomes 8, that becomes 4, and 44. So this is the real calculated altitude that we should see on this position. Now we measured this one. So we measured a slightly bigger altitude than we should have. So that means that since we have a bigger angle, a higher altitude than we should, we are closer. How much closer? Well, let's compare these two. Take the bigger figure up here, 44.57, and the smaller figure there, 44.48. And let's add these together, let's subtract these. So that is a 9, and that is a 0, and that is a 0. So we have 9 minutes as a difference, and 9 minutes means 9 nautical miles closer. So write 9 nautical miles as the intercept. Now how about the azimuth? Well, the azimuth is almost 118 degrees. We're not quite there. 118 degrees is again southeasterly direction. Does that make sense in the afternoon that we have southeasterly direction to the sun? No, it doesn't make any sense. And if you don't really follow if it makes sense or does not make sense, you can also follow the template here. So if the local hour angle is bigger than 180, it is the azimuth, meaning it's in the morning. But 43 is less than 180, meaning we are in the afternoon. So if 43 is less than 180, yes it is, we have to take 360 degrees minus 118. So we deduct this here. So this 2 to 6 is 4, 242 degrees. Well, that makes more sense because 240 degrees is southwesterly direction, or west-southwest. And that is where we have the sun in the afternoon. So that's the azimuth, 242 degrees. So now all we do is we have to draw it into the chart. What do? We take, this is just a sketch. In real, you take, of course, a real chart, or if you don't have one, you use a plotting sheet, which you will use in another chapter. But the principle is you mark this position into your chart. So this is the latitude, 56 degrees. You mark your longitude, which is 17 degrees and 30 minutes east. This is north. That is your assumed position or working position. At this point, you should have measured this angle, and you should see the sun in that direction. Well, let's draw the sun in that direction. First, here, this direction here is the sun, 242 degrees. Now we are closer to the sun. We are not here, we are closer to the sun, close to the sun. How much closer? Well, 9 nautical miles. So So this part is 9 nautical miles. This is not our position, never forget that. This is not a position, this is a position line. So we are somewhere along this, and you can draw 2 arrows pointing towards the sun. So we don't know where we are only approximately here. So if we take a noon sight and get a latitude, or a second shot a couple of hours later, we would get a second position line, and when they cross, that's where we are. So I think you could have somehow understood how fast it goes to come from here to there. So it's just a couple of minutes actually. It's 10 to maximum 15 minutes if you have some if you've done it a couple of times. So it's quite fast. And what else should you do when you're out sailing on a beautiful day and you've had your cup of coffee? Why not shoot the sun, sit down, do some calculations while making sure that you don't get seasick. See you in the next chapter.